In your textbook and the chapter overview video, we've discussed the strong evidence indicating that black holes really exist. But what exactly is a black hole, and what would it be like to visit one? We'll consider these questions in this video. The idea of a black hole was first suggested more than 200 years ago based on the possibility that there might be objects with an escape velocity greater than the speed of light. Recall that escape velocity is the speed that an object must have in order to leave orbit of a planet or other object. For example, the escape velocity from Earth's surface is about 40,000 kilometers per hour, or 11 kilometers per second. However, if we could somehow shrink Earth in size, the strength of gravity on Earth's surface would grow stronger, making the escape velocity larger. In principle, there is a size at which Earth's mass would be so compressed that the escape velocity would exceed the speed of light of 300,000 kilometers per second, in which case not even light could escape from the surface. This captures the basic idea of a black hole as an object with gravity so strong that not even light can escape from it. The boundary within which light cannot escape is called the event horizon, which marks the place at which the escape velocity is the speed of light. However, rather than being the surface of a highly compressed object, the event horizon hides everything within it, and all the mass has in principle been crushed to the point we call the singularity. Moreover, we now understand black holes in terms of Einstein's general theory of relativity, which tells us that gravity causes distortion of the structure of space and time, or space-time. We cannot visualize all four dimensions of space-time simultaneously, so we instead use two-dimensional analogies. We begin with a flat rubber sheet, representing space-time far from any massive object. A massive object, like a star, causes space-time to curve, much like the rubber sheet would curve with a heavy ball placed upon it. The denser we make the ball, the more it will curve the rubber sheet, and in our analogy, a black hole is a bottomless pit in space-time, with the event horizon marking the boundary from which nothing, not even light, can escape. Keep in mind that the rubber sheet is only an analogy meant to illustrate the extreme distortion of space-time near the event horizon. In reality, a black hole is spherical, as we see in this computer simulation looking toward a black hole with stars behind it. The strange arcs of light and double images of stars are caused by the way the black hole distorts space and time. We usually describe the size of a black hole by what we call its Schwarzschild Radius, which is the radius its event horizon would have if we neglected the distortion of spacetime. It is given by this simple formula, 3 kilometers times the mass of the black hole in solar masses. For example, a 10 solar mass black hole would have a Schwarzschild radius of 30 kilometers. Before we continue, check your understanding of the formula, which we have moved to the bottom of the screen, by answering this question. What is the Schwarzschild radius of a 1 billion solar mass black hole? Would it be 1 billion kilometers, 3 billion kilometers, 300 billion kilometers, or 1/3 of a billion kilometers? The answer is B. We simply put in 1 billion for the mass in solar masses, and multiplying by 3 kilometers gives a Schwarzschild radius of 3 billion kilometers. We chose these examples to illustrate the fact that there are two general categories of black holes known to astronomers. The black holes that form when massive stars die in supernova explosions typically have Schwarzschild radii of tens of kilometers, or roughly the size of Rhode Island, the smallest state. But we also find supermassive black holes in the centers of galaxies, and some of these have masses a billion or more times that of the Sun, giving them Schwarzschild radii as large as the orbits of the outermost planets in our solar system. For our final topic in this video, let's turn to the question of what it would be like to visit a black hole. We'll assume you are visiting a black hole formed from the death of a star, and not in a binary system like Cygnus X1, in which radiation from the accretion disk might quickly kill you. This animation imagines that you are orbiting the black hole while another spaceship is falling toward it. Notice that as you watch the second spaceship, you'll see its time run slower and its light become more redshifted as it approaches the event horizon. In fact, you'd never actually see it reach the event horizon because its time would in principle come to a stop at that point, and its redshift would grow too large for it to be observed by any conceivable technology. However, a person in the spaceship falling toward the black hole would not notice anything strange about his own time, and in fact, he'd very quickly fall past the event horizon and into the black hole. Unfortunately, he would not survive the journey, because the enormous mass and small size of the black hole means that gravity would be significantly stronger at his feet than his head, creating a lethal tidal force. The only known way that a person could in principle survive the journey across an event horizon would be if the visit were to a supermassive black hole, where the larger size would mean a much weaker tidal force. Still, according to current understanding of physics, no communication is possible from inside a black hole to outside it, so a traveler who crossed the event horizon could never tell the rest of us what he saw inside.